All right. All right, all right, all right. So, no jokes. This is a software architecture global summit by Geekle and 2026 for sure. And yeah, let me pull up actually the branding. I hope this one will work or not. Yeah. So maybe later. Thank you, everyone. Thank you for waiting. Thank you for asking, for commenting, for waiting for this great opportunity to learn from great experts from the community. Lately, what I was thinking is, man, the times are changing dramatically because today, in the era of generated code, like everyone who codes or generates code or vibe code or builds software, they need to learn software architecture actually. Because if we don't actually code manually, we architect, we make decisions. And how we do that if we actually don't know the latest and greatest practices about that? So uh, probably Gitl will switch this domain of software architecture summits to something broader. I don't know because honestly, I don't know how to differentiate now. If previously we had two tracks, one track is for juniors, which like super, I don't know, light and novice topics and nothing deep, and another one that was for experienced architects. So now I don't know because those who vibe code, they want to know about like all these deployment schemas. They want to know about cloud. They want to know about the design, the everything, because they actually move on on high level speed and no. And lucky today, I have great speakers on my backstage, and I am delighted to invite you guys to my stage. And hello, hello, hello. Let's see who we have. Asif, hello, how are you?
Yeah,
Can you hear us?
yeah, I can hear you. I'm fine. How are you?
Yeah, good. I see you are rushing to your place.
I
Great.
was just my meeting had ended another in the office. So
No worries, no worries. It's okay. And I see Raj. Hello, Raj. How are you?
Hey, hi, I'm good. How are you?
Doing great, actually. Excited to hear what you guys have for us. And also, I have Nikita. Hey, Nikita, how are you today?
Yeah, hi, hello, fine, thanks. How are you?
Wow, so great to have all you here. And yes, let's get it started. As always, we have this small talk, hello, intra chat between all four of us. Then we go backstage and I play our pre-recorded video sessions, and then we come back together and discuss everything and answer questions and basically having all that community fun, right? And why don't I just start with this simple question? Do you guys generate code or you still actually do it manually?
yeah, we generate. I
I
think I
see you
generate.
smile.
Yeah,
Yeah,
We, I,
go on, go on. Who first?
yeah,
Yeah, go on as if you were first.
yeah. So yeah, I generate code obviously. Like for the last 6 months at least, I've started generating the codes. I think I can say most of the codes are generated right right now, right from start to end. Even the small methods, how to even if you want to have a big method, you want to refactor this and all those like in daily way I'm using to generate the codes. Yeah, that's
Right. And you, Raj, what's percentage of your code is actually manual still?
Actually, I use mixture of both generated code and use Claude for assistance. So basically, the area that I find, all these assistants helpful is mostly data analysis, right? So you have a lot of data in, like, obviously all of us would be encountering in our day-to-day life, right? So to analyze those data, all complex data, right? Claude does it. I mean, you will be amazed like how well it kind of analyzes it and presents you in a way that you can, take forward your approach. So that's where I use most of my assistant. And for coding, yeah, we use here and there, like, but mostly for, yeah, understanding if, say, legacy systems or the new code bases that you're not aware of, that has sped up the process. But I would say data analysis, while to make our job as an MLE easier for us to build models.
Right.
So that's where I find it the most helpful.
But you don't do the front end code manually, don't you?
So I don't work on front end per se, but like for demo, right? If I have to make a demo, like for example, if I'm working on an evaluation pipeline or if I'm working on a retrieval pipeline, and then if I have to do a quick demo to something, then having that, that assistant, clause assistant to just spin up a simple Streamlit UI, that helps, right? Yeah.
Right, right, right. And yeah, and Nikita, for you.
Yeah, from my side also, I prefer to use some kind of mixture, and I use AI code mainly for prototypes, for checking some kind of hypothesis, and also I'm actively using Claude as a sparring partner, not only with the code, but with different ideas. Hey, I have an idea. Let's challenge it. Disagree, agree. It's rather useful, but I am, let's say, far away from committing this code to production because, from my perspective, it's it's not a good idea to. But yeah, to prototype, to understand, to check, it's pretty good. It's useful.
Do you mean actually, all right, you vibe coded the prototype and then you actually, if it's viable and your stakeholders say, yeah, go on, we want that. So you go back and actually create all those layouts and everything manually again?
Yeah, definitely. So in any case, we are trying to reuse this, let's say, code base as an initial point to enrich this with some kind of manual paths, and yeah, but production code should be written, should be reflected through some kind of, let's say, additional manual checks.
All
And
right,
I
so
hope
then you
that
go back.
and I hope my developers are not using wipe code, at least in the production.
And then you go back and get your hands dirty and read all over. Okay, cool. You probably work on some highly regulated or high risk
Yes,
sphere, right?
definitely, yeah, definitely. I
Yeah.
suppose it's
What
the
do you
main
do?
reason.
Just remind us.
Industrial automation, so just bringing AI to the factory floor. That's why it's rather highly regulated sphere and rather critical sphere. That's why it's not affordable to use just to blindly use vibe coding in our tasks. That's why it's
Okay.
more or less useful. Mhm.
So you're still safe, guys.
Yeah. Yes. At least we are trying to save this world.
All right. All right. Okay, cool. Thank you very much. And the next question is, how do you use actually AI for architecture design? Do you actually do that? What's your pipeline? What's your best practices? Maybe you already have this sequence of actions that normally leads you to the best architecture, or you still using your, like, I don't know, mermaid diagrams or whatever, just to do it manually.
From my side, I can start. So first of all, as I already said, I'm trying to use AI stuff, AI LLMs as a sparring partner. For instance, I have such kind of task my approach this and this. Uh, Try to, I don't know, try to disagree with me or try to challenge this idea. It's the first approach. And definitely I'm using this LLM stuff to generate mermaid, to generate all these, let's say, all these artifacts, but just to make this mechanical work, not to do some kind of design instead of me. So
Right.
help me to come some kind of conclusion, and then help me to make this mechanical work to generate different, I don't know, plant to mail, mermaid, and all this stuff. So
Right.
rather useful.
All right. And you, Raj?
Yeah, so basically I use AI tool, to quickly, basically, if I have to do a quick prototyping, right, and then do some initial any testing on the validation checks that I need to in the prototype. So in terms of architecture, what I basically do is I mostly define some requirements that I might have, pass it to the AI, and then ask it to maybe generate initial architecture or drafts that I can find helpful. I can also provide them the architecture that I want in the prompt, right, and then look at the inputs that the AI is suggesting. So I can, that helps me to manually review it, and also align with whatever best practices that will be helpful for scalability and maintenance, right? So yeah, so that's what I do mostly. um Basically start with a prototype, give some constraints and requirements to the AI, and then and also get the architecture that they are suggesting. So I think I would say, like, having this hybrid approach is very useful, because I have tried, in my own personal capacity, I have tried some of the designs, like just ask randomly, give a problem statement, ask the AI to answer, and then you would be surprised, that the AI doesn't understand the whole full complexity of what you want. So there is always a hybrid approach that keeps happening, right? So you need to provide with the initial architecture, or at least some of the layouts that you want, and then you can leverage AI for efficiency. So that's what I find
Thank
useful.
you. Thank you
Safety
very much. Yeah,
approach of
that's
AI.
cool. Yeah, and Yosef.
Yeah, I also feel like same way. Like using AI, you need to give some starting point to them. You just can't blindly say let's do this. And some of the times that I mostly also use it in debugging some issues which has like touching mainly different teams code, and like you want to communicate with team, they might be busy and all those type of things. Then probably I use like, okay, this is where my debugging is telling me there. Can you please tell me how I can move forward? Where in that code it is touching, or what all files or method it is doing? So that it can help me understanding those part of the course which I am not aware of, and other team might be busy and can take a long time. Previously it can take a long time because you need to wait for a meeting and all those type of things. But now with this, I think it has helped a lot. So apart from like designings and all those things, I also like heavily in the debugging things, where previously it used to take a lot of time because you are dependent on other folks, but now you can be much more self-independent.
Right. And do you guys use any AI tools for creating those diagrams? Like, you choose, you have three different paths, and you choose this path, and it goes and gives you different options, and you click here and it gives you different options, and you explore and you challenge. Do we have all this magic already in these diagrams, or not yet?
So I can go away. Like in Meta, everything is like internal. They have MetaMet and all those things. Yeah, and they recently bought Manus, a new AI thing, right? And I feel that Manus is pretty good in this generating PPT things and diagram and all those things. Like even for the PPT that I shared for this presentations, I heavily used those things to give me the slides and all those things. Like I told them, like, this is my resume, this is what I want. Can you generate a basic slide which on top of, and it gave a pretty good slides to work on. So I think that is where it has become very good. And then there's another internal to the MetaMate, which they have integrated with cloud and all those type of things. But most of the things are internal. Like they have integrated this tool as well in the IDE that can have different context, more context about the code. And there's like a browser link as well that will have much more internal sources of posts and all those type of things. So context can be different based on where you are using that same tool in different tools. So yeah, that's what we have. And
Yeah, sounds like next century. Okay, and who's next?
Yeah, so for me, I haven't personally used fully interactive AI tools specifically for architecture design. Mostly, I've used tools, that generate static designs, right? Like Mermaid or something like that, based on the prompt, or interactive sessions with the AI. But having an interactive AI tools, I haven't personally, used in terms of architecture. Yeah.
Yeah, cool. Yeah, okay, and maybe you, Nikita.
No, I already shared. So from my perspective, I'm only using just
All right,
interactive mode to build
conversational one.
mermaid and all this. Let's say not sophisticated stuff. And I
Okay,
prefer to
yeah,
double check to double check, not to trust fully on AI because sometimes it's
right, right,
rather
right, right.
critical.
Okay, cool. So why don't we just say thank you for connecting to you all, and jump right to our sessions we are waiting for, because I have something incredible today. Let me pull it up right here. Yes, I see it right now. Okay, so. Yeah, and only one disclaimer, Raj. Your session, I wasn't expecting for that. It was 1 hour long, and we cannot afford actually be listening in this session for 1 hour. So I'll try to cut it down to like
Sure.
25 minutes or something. And
Sure.
but you can be sure that community has access to your full file. We just can't wait for 1 hour today. Okay,
Yeah.
so here's the play. I will do these 3 sessions and invite you back, and we will discuss it. Okay.
Yeah. Sure.
Yep,
Okay.
sure.
Cool. All right. Thank you very much, and dear audience, let's jump to our first session. Our first session comes from Raj Shah, working for Apple, machine learning engineer, talking about bridging the trust gap in AI system, ensuring reliability and safety, which is quite, crucially important. And let me pull it up.
Hi everyone, I am Rajeshwari Sa, and today I want to talk about what I believe is the hardest problem in applied AI right now, which is not making agents work but making them trustworthy. Over the past years, we have seen incredible advances in what AI systems can do. They can reason, plan, call tools, coordinate workflows, and produce output that look remarkably like real human work. And in demos, they often feel magical, but something very important changes the moment you move from controlled demo into production. So in production, you don't control the inputs, you don't control the edge cases, and you don't get to pause the world when dependencies fail. And you definitely don't get to ignore cost, latency, governance, or any risk. So, today I want to explore what I see as the largest unsolved challenge in applied AI, which is the gap between capability and reliability. Also, if you want to follow along with the code behind the system, I have referenced my GitHub here. And the repo is Medical Scribe Agent, so you guys can take a look at it. So, before we talk about the architecture, let me start with a simple question, which is what exactly happens when an AI system is wrong? So, in some domains, it's inconvenient. Maybe a summary isn't perfect. In others, it's inexpensive. A bad decision can cost real money. And in few domains, being wrong stops being a quality issue, and it becomes a safety risk. So rather than start abstractly, I let me begin in a domain where reliability is non-negotiable, so which is the clinical domain, right? So imagine an AI system that is listening to a doctor patient conversations and automatically generating a clinical note. The note is flawless, structured, coherent, and billable. From the surface, it looks perfect. But there is just one problem. The diagnosis it documented never actually occurred. The error isn't cosmetic, it becomes a part of medical record, and it can influence treatment decisions, billing, legal defensibility. This is what a capability reliability gap is, and it's the gap that we need to close if AI is going to become true production infrastructure. So now you don't need to work basically in healthcare to care about this. The same reliability patterns shows up everywhere in finance, in compliance, incident response, developer tooling. Basically anywhere a multi-step step agents enter operational workflows. Healthcare is just a domain that makes the consequences obvious. So uh, today, capability is accelerating at an extraordinary pace. Models are improving in reasoning, planning, tool use, and autonomy, but reliability is lagging. The reliability looks very different in practice. It shows up in silent hallucinations, output that are fluent but they are subtly wrong. There is schema drifts, output gradually stops matching downstream contracts. There is tool fragility. One API can break an entire workflow. And there is non-determinism. So the same output produces different outcomes. So the same input produces different outcomes on different days. So here's the framing I find helpful. Capability is what a system does at its best, but reliability is what it does on a random Tuesday at 3 a.m., right? So production systems are judged by their worst day and not on the day of their best demos. So so this is why the talk matters most now, which is like now that AI has crossed what I called a demo threshold, we already know that these systems can impress us. Now they must cross the trust thresholds, right? Across industries, we are watching a shift right now. So co-pilots are becoming operational workflows, assistants are becoming decision systems, experiments are becoming dependencies. And once a system becomes a part of dependency chain, failures stop being embarrassing. They become expensive, financial risk, operational risk, regulatory risk, and sometimes even safety risk. This is why reliability is rapidly becoming a defining engineering challenge of applied AI. So, how do we go about designing this system, right? So, if the models are inherently probabilistic, the question naturally becomes like, how do we build systems that behave predictably? Uh, Now, let's go back to our clinical note example. If we know models can hallucinate, we cannot simply hope that the clinical note that it wrote is correct, right? We need the architecture that prevents bad informations from ever reaching a medical record. So, in production systems, we don't rely on correctness, we rely on constraints, right? So, schema is what comes first. We constrain a problem. A schema defines what a clinical note must contain, which is things like symptoms, medications, allergies, vitals. Without this structure, the model has infinite freedom. With structure, we bound the space in which it can be wrong. So we give them that space. Then is agent, right? So inside that boundary, the agent generates structured output, but we treat the model as failable component, not an oracle, right? So, but it is acting within the boundary that we created, producing the output within the boundary that we have given. Then comes validator, right? We verify it. If the agent documents an allergy, the validator should be able to point to the exact transcript uh, span that is supporting that. So if we cannot do that, the note should never reach a physician. Then comes like one of the important stuff in this design is the state, right? We also maintain a shared state, the single source of truth, the transcript, the extracted entities, the soap drafts, the validation flags. Every agent reads from the same reality. This prevents the drift and make the system more observable. And finally, we measure the behavior across many encounters. So, are hallucination rising? Are required fields missing? Is human edit distance increasing? So, evaluation is what keeps the reliability from silently degrading over time. Uh, the model is least reliable component in this system. So, we cage it in a deterministic infrastructure. Reliable AI does not emerge from better prompts. It emerges from system that is designed to constrain, verify, and measure probabilistic behaviors. So next thing is like once we wrap these probabilistic models in deterministic infrastructure, we dramatically reduce risk. But to understand like why this matters, we need to talk about how failures actually behave in production systems. uh, which is when most people imagine systems failures, they imagine crashes. Something breaks loudly, alerts are fired, engineer get paged. But in AI system, especially multi-agent ones, the most dangerous failures are often very silent. So it often starts with something very small, maybe the transcript slightly misheard a phrase, not completely wrong, just ambiguous. And this ambiguity flowed downstream, right? The extraction then interprets it, but now it makes a subtle mistake. By the time we reach a clinical note, the system may confidently document something that the patient never actually said. That incorrect statement influences coding, billing coding, which leads to denial of insurance and eventually financial impact. If you notice, nothing crashed, the system functioned perfectly, but the outcome degraded step by step. Reliability here, like reliability failures don't announce themselves, right? They cascade quietly. And this is exactly why architecture matters. Without validators, without evidence check, without a shared state, a small upstream error can become a permanent part of a medical record. And in complex systems, a risk is multiplicative, it's not just additive. Think it of like a rounding error that propagates through a financial system, tiny at start, massive by the end. And our job as system designers are not just to prevent large failures, it is to stop small errors from compounding. So like, yeah, so far we have just talked about how failure cascade, right? But there is another dimension that we need to consider, which is what is the cost of being wrong. Like, so not all AI errors carry the same weight. For example, if a movie recommendation is slightly off, nothing breaks, right? If a production description on a website is awkward, it's mostly cosmetic. So many system can tolerate like small mistakes, but like as AI move into operational workflows, the tolerance for error collapses, right? Because the consequences, like the consequence changes. Uh, uh, like for example, an elucidated diagnosis is not a typo. Like if there is any missed allergies, that's not very cosmetic, right? An incorrect dosage is absolutely, it's not an inconvenience, rather it's a very big liability, right? So when the cost of being wrong rises, we need to change the architecture, right? So in low risk system, we optimize for speed and capability, but in high risk system, we optimize for predictability and control. And like clinical documentation lives firmly, I would say, in the second category, where we optimize for predictability and we're optimizing for control. And these nodes influence, because these are the nodes that influence treatment decisions, right? They become part of legal medical records. They're affecting billing and compliance, and once they are recorded, they are just difficult to unwind. So basically, this is the moment where AI stops being a demo, and it needs to start becoming infrastructure. And infrastructure that it carries a totally different expectation altogether, right? It has a very different expectation. It must be, an infrastructure must be dependable even when components are imperfect, right? Safety is not something that you can add later. It is something that you need to design from the beginning. So the question is no longer like, can we build agents that work? The question now becomes, what architecture ensures they fail safely, right? So uh yeah, so once reliability becomes a safety concerns, we can no longer treat, architectures as an afterthought, right? We have to design for reliability from the very beginning. So let's make this, very concrete. I want to like walk through a design posture behind clinical grade agent systems. So when the cost of failure of like is high, the reliability cannot be, retrofitted. First, there is structured outputs, right? Free from text, like free form text is very powerful, but it's very difficult to govern. And structure creates boundaries, and boundaries then reduce risks, right? Secondly, it is auditability. One of the most important requirement is auditability. So in high stake workflows, it is not enough for a system to be correct, right? It must also be defensible after the fact, right? So every claim should be traceable to the evidence. Third and most important is validation, right? So we should never assume correctness. System must actively check their own outputs before the outputs enter the durable records, right? And finally, we also have human oversight, right? So autonomy is powerful, but accountability still belongs to human, especially in regulated domains. So the design goal is not blind autonomy, it is like safe acceleration. So instead of asking, can we build agents that write nodes, we need to ask a different question altogether. Like, what architecture prevents bad information from reaching, ever reaching a medical record, right? That's the question that we need to ask. Yeah. So so what does it actually look like to design for reliability from day one, right? Let's walk the system. Notice, like, this is not like a prompt, right? It's an assembly line, and an assembly line exists only for one reason here, which is to reduce the variance, right? We begin with raw conversation between a physician and a patient, and it's messy, right? It's unstructured and it's inherently ambiguous. So our first task is not intelligence, it's mostly stabilization, right? Then there is transcription that converts the speech into text, but we treat it as a fallible component, right? Like fallible component, not the ground root. Next is we extract structured clinical entities like symptoms, medications, vitals, etc. This step is very critical because structure bounds inference, and the smaller the space the model operates in, the spacer the system becomes, the safer the system becomes. Only after we establish structure do we allow a system to generate a uh, narrative draft. Sorry. So notice the order here, right? The structure first and reasoning second. So before anything reaches a physician, we introduce a consistency validator. So the main job is skepticism, right? uh yeah, it that's what it is doing. So does every diagnosis have evidence? Does medication is the Are the medications consistent? Are contradictions present? And if there is no validator, then there is no record. And finally, humans remain in the loop, not because the system is weak, but because accountability still belongs to people. So reliability is rarely a result of one smart component. It is the result of many modest components which are carefully arranged. So behind this flow, all of this flow also sits a shared state, which is a single source of truth. So every stage reads from every state, every agent reads from the same reality, right? This prevents the drift and make the system observable. In reliable system, the responsibility is never ambiguous. Every stage has one job and one job only, and this is how we stop small upstream errors from cascading into durable records. So reliable AI is not about smarter prompts now. It's about like safer systems, and this leads to a very critical mindset shift. Like stop asking questions like what prompt. Instead, we need to ask questions like what guarantees, right? So that's a very important mind shift. So once we see architecture this way, something deeper begins to shift, right? The question we ask as engineers starts to change, right? As I said, we stop asking what prompts we should use and start asking like what guarantees must this system provide. So prompt thinking is naturally very exploratory. We try something, we iterate, we refine, and then like that works. All of this works very beautifully in demos, but then production systems require a very different posture, because production is not about what works once, it is about what works predictability, right? So prompt thinking asks like, will the output look good? And system thinking is like, under what condition could this fail, right? Prompt thinking hopes for correctness, but system thinking actually engineers for safety. And reliability begins when the behavior becomes enforceable. So let's return to our clinical note example. So instead of asking like, can the model generate a good note, we asked questions like, can a diagnosis appear without evidence, right? So can the required sections be omitted? Can contradictions slip through? And most importantly, like what prevent these things from happening, right? So basically, hope is not a reliability strategy. Reliable systems are not like defined by what they do, but what they refuse to do. So basically, guarantees are properties that you can test. For example, diagnosis must have supporting evidence, right? As I said, required fields must exist. Whatever is required in symptoms, in vitals, must exist. Unsupported claims must be flagged. Like if something is unsupported by any, so if a claim is unsupported by any of the entities, then it should be flagged right there. And then when guarantees, so basically when all of these guarantees exist, then the behavior becomes more predictable. So this is how constraints turn probabilistic models into dependable systems. And basically prompt, they influence behaviors, but then having an architecture, it constrains behavior, and constraints are what makes systems trustworthy, basically. So now the next question is like, how do we reduce the uncertainty, right, inside the system that we want to develop? So yeah, so exactly. So once we like kind of begin thinking in guarantees, another design principle becomes like very unavoidable, which is we must reduce uncertainty wherever possible. So we need to decompose to reduce entropy. So early agent system often, followed a very natural path, which is give one agent many responsibilities because it feels simpler. One large prompt, multiple tasks, like single output. I sometimes call it the YOLO agent. Basically, the problem with this monoliths isn't like that they fail. It's that when they fail, we don't know why, right? Was the reasoning flawed? Did the model misunderstand context? Did it hallucinate? Or did one task interfere with another? So when like this responsibility is kind of blurred, debugging also becomes a guesswork. So instead what we do is we decompose, right? So we have multiple different decomposed agents, right? So a transcription listens, an extraction structures, a summarization organizes, and a validation enforces connectness. So every component has one job and one job only, which means like fewer responsibilities per component, which means lower variance, and lower variance is the foundation of reliability, right? So in our clinical system, this separation is very critical. We never allow the same agent to both interpret evidence and validate its own claim. Skepticism must live outside generation, right? So reliable systems separate creations from verification, and this decomposition also sync the blast radius of failure, right? So we, if extraction makes a mistake, the validator catches it. If the error doesn't propagate, the so this complex system becomes safer when complexity is kind of partitioned, right? So I have like to give an analogy, like because the airplane don't just rely on one computer, they rely on redundant systems, right? So decomposition doesn't becomes decomposition doesn't just like doesn't eliminate failure, it makes failure understandable. And once a failure is understandable, it becomes manageable. But decomposition also introduces a new challenge, which is coordination, which raises the question, right? How do we ensure that every component operates the from the same reality? Correct. So yeah, so as I said, like the decomposition makes system safer, but it introduces a new challenge like coordination, because once you have multiple agents, you must ensure that they operate from the same reality. The shared state is what create a system coherence, and without this shared state, every agent builds its own interpretation of the world. And the moment interpretation diverge, reality begins to erode. And imagine one agent's extract allergy but another agent doesn't see it. Now your system holds two conflicting realities, and in clinical workflows that is absolutely unacceptable. So the transcript becomes durable context, not something each agent like interprets independently, right? So in the example here, we have used medical scribe state as a central state object, and this is shared across all the agents, that we have: the transcription, the extraction, the summarization, and the validator. All of that share the same state. So the structured clinical entities, all of them, they live here. Every component references the same facts. The generated node is written back into the state, making it more observable and reviewable. And if something looks suspicious, that signals that's one second, my battery is low. Yeah, sorry. So if system looks suspicious, that signals becomes part of the shared reality, right? So nothing important lives only inside one agent. Instead, the state, this shared state is not just a mere programming convenience, it is also a reliability mechanism, right? So when the state is centralized, we gain traceability, observability, and most importantly, we also gain reproducibility, right? So reliable systems minimize hidden knowledge. If any critical information exists only inside a prompt, only inside temporary chain, or only inside one agent, then debugging becomes nearly impossible, right? Where will you be debugging all of this? This is where like shared state is one of the most effective ways to stop small errors from propagating. Basically, healthy distributed systems converge on a single source of truth. So think of it as a database with strong consistency guarantees, and everyone reads the same record, right? So when every agent sees the same reality, coordination stops being fragile and reliability starts being scalable. But the shared state alone isn't just enough, right? Because when the agents agree, we still need to know where did all this information come from, right? So that is where trust, it starts demanding traceability, right? So shared state gives us coherence, right? But this coherence alone is not enough, right? Because even when agents agree, we still need to answer a harder question, which is, where did this information come from, right? In high stakes systems, correctness is not just assumed, it must also be defended, right? So suppose the note says patient reports chest pain for 3 days. That claim must map to an exact transcript span, right? Not approximate, not implied, but it should match the exact claim. So if that claim cannot be traced, it cannot be persisted, right? So basically, traceability transform generative system into accountable system, and make claims also auditable. It makes review efficient, and it makes errors visible, right? So in clinical documentation, this is very essential, right? So physician must be able to verify statements quickly, compliance team must be able to audit records, and if something is questioned later, the evidence must already exist. So trust is not an architecture strategy, right? Traceability is here. So when system generate a text without evidence linkage, we introduce uncertainty, and we don't know what is real and what was inferred. So traceability is how we enforce guarantees. So basically, a diagnosis without evidence is not a diagnosis altogether, right? It is a failure. So reliable system minimize any unsupported assertions, and this is how we shift from probabilistic storytelling into a structured accountability. Generation is very powerful, but verification is sovereign. And once we begin requiring evidence, the next logical step is very obvious, which is reduce the surface area where unsupported claim can actually emerge, right? That is a very obvious thing. How can we reduce that surface area, right? So basically, yes. So once we require evidence for every claim, a natural question can be like, how do we reduce this unsupported claim from appearing in the first place, right? So that is where structure before reasoning comes in place, right? So large models are extraordinarily capable, as we all know, but when given unbounded space, they will infer, and inference is powerful, no doubt, but inference is also where all the hallucinations live. And we move directly, if we try to move directly from conversations to narrative, the model must decide what matters, what doesn't, and what was implied and what was actually stated. So this is an enormous cognitive surface, right? So instead, we structure first, right? So we begin by extracting discrete clinical entities, right? So symptoms, medications, allergies, vitals. Then we validate them against a schema, which is a required field text, right? Formats we have.
I'm sorry, I hate to do that, but I can't play it in full. So we now have the amazing actually understanding that Raj knows something about that, right? And really deep. And I invite everyone to actually watch in full this session on our platform. So please do pay attention. Anyway, we are moving on, and our next speaker is Nikita Glovko. He works for Siemens as portfolio architect and talking about beyond the black box agility in AI architecture with domain driven design. I am sure we heard a lot about this domain-driven design um, concept and everything, but AI comes and how it changed things. That's what we really need to learn. So let's do that.
Hello, dear colleagues. My name is Nikita, and I am AI portfolio architect from Siemens, Germany. Nice to meet you all, and it's a big pleasure for me to be here. So, beyond the black box, we treat AI system as a black box twice. Once because we cannot explain what the model is doing under the hood, and again because we cannot change the system around it. And today we will try to fix the second issue with a proper architecture. Okay, I suppose everybody saw such kind of message in their email box with the request from their colleagues. This request is completely reasonable because, for instance, throughput is suffering, and this colleague is asking not for a new model, but she's asking to make a small change with a threshold to change it from 90% to 85, just 5 points. And you know this confusing feeling because you know that this simple is not really simple, at least not in your system. And let me show you why. So you get this message, and the first question, where does this threshold even live? Maybe it's somewhere baked into a model training. That means that you need a whole ML team you need to retrain, which will take around 3 weeks minimum. Maybe it's somewhere in a post-processing, but in which script, who wrote this script, what else does it touch, or maybe even it is somewhere in a business service, but which repository, who owns it, again, nobody knows. And even if you will find it, you need to figure out what breaks when you change it. Does it affect all your models? Again, usually nobody knows because nothing is explicit. And even after this, you need an alignment meeting. You need to perform an impact assessment. You need to implement a testing cycle. You need a deployment window, which means that your colleague expected this feature at the end of the day, Friday, but reality, you need 6 to 8 weeks just for a 5-point change. And the problem is not with your team. You have a perfect team. The problem is with your architecture, because somewhere along the way, we have merged the business decision with the technical implementation, and now they cannot move independently. And today I will show you how to separate them with the 3 boundaries. And such kind of changes will take minutes or hours instead of months and weeks. Okay, 3 boundaries. Each one unlock a different kind of agility. Model boundary, so data scientists can ship a new version of model while the rest of the team is doing refactoring, is doing some kind of another technical stuff. Data boundary, so feature change will not break unpredictably every downstream system. Decision boundary, your colleague can change that threshold on Friday without a retraining, without redeployment. But yeah, let's start with the first one. The first one, it's a model boundary, or how to isolate your AI logic from business logic. Okay, let's look at what happens when this boundary does not exist. Some of you will recognize this code. Here we have a quality processor, which is pure business logic, which imports XGBoost directly, which knows the model path, which also handles tensor shapes, and also has this threshold hard-coded. And here's a smell test. If your business code import ML framework directly, if you see something like import Torch or import XGBoost, in your domain service, it means that your boundary is leaking. So how do we fix this? The answer comes from the pattern we've been using for a long time, for a decades, for a software architecture. It's supporting adapters. And in this case, domain layer speaks business language. It knows about production segment, inspection decision, defect detection, and it has no idea about XGBoost or other ML stuff. The adapter layer is where your ML and AI logic lives. It implements a defect detector interface using YOLO TensorRT. It handles tensor shapes. It loads model files, and all the complexity of AI is implemented here. So now you can replace your XGBoost model with neural networks, with rule engine, or with third-party API, and your domain is stay clear, and you just call a respective interface. Okay, now let's make this concrete. What does the contract between these layers actually looks like? And here, what a good contract should include. So input is a stream segment, is a domain object, not a numpy array, not a list of features. The output is a defect result, also domain object. It includes scores, confidence, model version, and even explainability factors. No mentioning of tensors, features, or frameworks. A product manager can read this contract, data scientist can implement it, and this is the power of ubiquitous language. But having a clean contract is not enough. In the manufacturing, you need to handle real operation concerns, timeouts, fallbacks, multiple models. That is where the inference gateway or prediction gateway comes in. So it handles everything the domain should not care about. For instance, routing, different paths should go to different models, timeouts, fallbacks. For instance, if inference falls, it should be rolled to manual inspection. And at the end of the day, it helps never stop the production line. And it also emit events, for instance, prediction completed for monitoring, fallback used for alerting, And this is how you know that your system is healthy. Okay, now we have clean contracts and operational resilience. But how do you know a new model is safe to deploy? This is where contract testing become critical. But the thing is that contract tests is different from unit tests. The typical model test answer a question whether it works or not, which is not useful for a contract use case. A contract test should verify promise, whether score is between 0 and 1, whether latency is under 100 milliseconds, for instance, and which is more critical, whether known defects are detected. Please run these contracts before every deployment, and then you will be on the safe side. Okay, let's recap what the model boundary gives us before we move on. So ports and adapters to keep ML out of your domain, prediction gateway handles operations, and contract stats verify behavior. With this boundary in place, your data scientists can iterate without coordinating with every other team. Okay, but where do the models get their inputs? That is where things often go wrong, and that is where our second boundary comes in. Let's start from the problem. Let me show you one of the most confusing bugs in manufacturing AI. It's almost impossible to debug. This is a training serving queue, the silent killer of industrial AI systems. Look, we have the same feature named physical position. In training, it computed offline from encoder logs with calibration and interpolation. But on the shop floor during the inference, it should be read directly from the PLC, and missing values replaced by zeros. We have the same name but different physics, and model was trained on one set of data X, but is inferencing on another one, which means that detection accuracy will degrade. We will have more false positive or false negative depending on your model, and which is more worse, that nothing will crash. You will see no alarms, you will see no stack traces, just a model quietly getting worse while the line keeping running. The solution is not about sharing code between training and edge, training and inference, because it will create different problems. The fix is to treat your data pipeline as a bounded context with its own language, ownership, and contracts. For instance, ship segment profile, it's a feature aggregate with related measurements that updated together, version together. It has an owner, quality analytics team, for instance. It has a version. When the team change, for instance, encoder mapping, they have to change the version. And downstream models choose when to upgrade, but not silently break. But not all features are equal. Some features can be pre-computed, cached, and they are stable. For instance, camera calibration, illumination profile. You should pre-compute them, update them in milliseconds, in seconds. It again depends on your system. But we have another class of features which should be fresh. For instance, encoder ticks, speed, temperature. These features should be computed in real time for every segment, for every product item, and so on. The model consumes both of these features, and it does not care where they come from. And your architecture should care a lot about this, because for offline features you optimize for correctness, for online features you optimize for latency. And in case you make a wrong decision, you will either feed your model with expired physics or just spend your real-time budget just for a computing feature that should be cached. Okay, but let's go back to the solution. Don't share code, just share the specification. So for instance, physical position in meters, it should be a float, it should be never null, it should be in a specific range, and so on. This is a contract between data science and implementation and operations. So for instance, a training pipeline can implement this contract in a Spark. Inference environment implements the same contract but in the C++. So we have different implementation, but the same specification and identical physics. And in this case, training serving queue goes from mystery to a non-issue. Okay, once you have specification, drift detection is almost free. For instance, mean position shifting, maybe it's fine because you're working with different products, but in case you see jumping from 1% to 7%, it's a real red flag because you either lose a cable, you have a PLC glitch, or maybe some kind of encoder misalignment. And the idea, you should be able to catch it on the data level more or less immediately before the model starts missing defects, not 3 weeks later when accuracy drops. Let's recap the data boundary before we move to the final one and the most neglected boundary. So split offline from online, use specification to eliminate skew, monitor for a drift. With this boundary, your data engineers can ship features improvement without coordination with other model team. Now, what happens after the model makes a prediction? When, for instance, model says 87% confidence scratch, what do we really need to do with this? And this is where the most systems fall apart. We have a critical gap between what model outputs, probability, and what the system should do, an action. And this gap contains a business logic, thresholds, rules, expectations, and context. When this gap is implicit and bottled in a if statements, nobody owns it, nobody can explain it, nobody can change it without touching the model. And that is why your colleague from the original letter can change the threshold from 90% to 85% by Friday. And the solution is to make this gap explicit, to give it a name, owner, a clear contract. So we call this a decision boundary. The decision boundary makes everything explicit. It takes 3 inputs: model scores, business policies, and the context specific to this request. It produces a decision, not just a proof or block, but also review. Human in the loop is designed in, not bottled on, and which is critically, it produces a reason. And now everybody can understand why model makes this decision, makes this prediction, and what is really behind this decision. Now let's look at what those quality or business policies actually looks like in a code. This is what threshold looks like when it's done in the right way. Policy object encapsulate business rules explicitly. They are named, versioned, owned. Threshold are configurations. For instance, your colleague from the original letter can change 0.9 to 0.85 without changing a code. A product manager can read and review these, and you can write unit tests for policies independently for any models. Okay, policies are great for making decisions, but in manufacturing, you also need to prove you made the right decisions. So that's where inspection records come in. Every decision produces a record like this, with the context in which this decision was made, model predictions, policies which were used, why, what kind of policies were used, and the final decision with a clear reasoning. And as a bonus, these records can be used as your training data for the next model iterations. Okay, but now people often ask about explainability in AI systems, but there are actually 2 different questions being asked, and they have very different answers. For instance, model explainability: why did the neural network output is 0.87? This is a data science problem. Sometimes it's hard to answer, sometimes it's even impossible. And decision explainability: why was this product blocked? This is an architectural problem, and it should be easy to answer if your decision logic is explicit. So you might not be able to explain why the model said, for instance, 0.87, but you should be always able to explain why this value lead to blocked, because the logic is in the code, not in weights. Let's recap the decision boundary and also remember the original request that we need to change our threshold from 90% to 85 by Friday. So with the decision boundary, that is a configuration change. You just need to update the policy, deploy it, or even make some kind of hot reload of this configuration, which can be done in minutes. And that is the agility we have been building toward. Okay, now let's pull all these three boundaries together and see the complete picture. This shows how all three boundaries work together. So data flows down through three boundaries context. Each context owns its complexity. Each boundary is defined by a contract. And the contracts are where you invest in stability. Everything else can involve. Okay, and this is an agility we have unlocked. Data scientists can ship models, update them in days. They just own a prediction contract. Data engineers evolve features over weeks. They own a feature contract. Product team adjust policies in hours. They own a decision contract. Everyone moves at their own speed. Contracts are the coordination mechanism, not meetings. So you have seen patterns, you've seen examples. Now I want to give you something concrete to do, for instance, tomorrow morning. So just pick one AI system and ask these three questions. First, can I replace a model without changing business logic? If not, your model boundary is leaking. Can I add a feature without changing model code? If not, your data boundary networks. And can I change a threshold without retraining? If not, you need a decision boundary. If any answers is no, it's not a failure, it's a discovery, and now you know exactly where to start. And before we wrap on, I want to leave you with one final thought. The goal is not to build a perfect AI system. Perfect does not exist. The goal is to build a system that can get better. So where can you improve the model, evolve the features, adjust the business rules? That is what beyond the black box really means. Not making the model transparent, but making the architecture transparent, so everyone knows where they can move freely and where do they need to coordinate. Yeah, that's all. Thanks a lot for your time. You can find my contacts on this QR code. Looking forward to your questions.
Thank you, Nikita. Thank you for sharing that. That was deep, actually. I didn't follow the half of that. Probably I should rewatch that. But thank you for sharing. It's very deep and interesting. And we're moving on to our next speaker, Asif Iqbal from Meta Software Engineer, with the presentation Modern Architectures for Scalable Systems. Let's do it.
Hello everyone, my name is Asif and today I'm going to talk about modern architecture for scalable systems. But first of all, to give an overview, I am Asif. I am a senior software engineer at Meta and I have around 13.5 years of experience. Before Meta, I worked with Google and Microsoft along with other companies. My whole experience lies in building distributed systems that scale to millions and billions of customers over the years. And the thing that I will talk about is not normal things that you can find on the internet, like how to build distributed systems, but how I have used those concepts along the time in my career. That's what I will try to focus on. Okay, so let's start. one of the challenges or the scale challenges that we faced, or that specifically I faced in my career, is like when right now at Meta, I'm working on the Meta VR things where you can go in an event and see the video playing in a real 3D format in a virtual world, which can be rectilinear videos, 3D videos, 180 videos in both 2D and 3D formats. The scale that we talk about is like playing video for 200,000 concrete users in an event that will be like across both VR and mobile. Second scale challenges is I worked on some personalized experience for Adobe products, and I've worked on providing a platform for that so that different products in Adobe can come and give some personalized experience to the users, like running a promotional campaigns for some users in US who are the first time users, let's say something like that. And that had like a scale of millions of real-time events per second for personalizations. Similarly, for Google Cloud, I was handling the billing systems, which was handling millions of transactions, and with billing, you need absolute accuracy. So these are scale challenges that we face today that I have worked upon. Okay, so what are the core challenges, the core principles? The core principles that is there, and we will talk in detail for each one of them. First is the separation of concerns, where like you decouple the things, right, from executions. Having a big monolith, you can try to have a small microservices if it needs. It makes upon your decision what you want to go with monolithic microservices, because you don't want to overdo anything. Second is the horizontal scalability. You have to design where each instance try to prefer to be stateless services, right, and try to distribute load across multiple processing units across multiple regions. Third is the asynchronous processing, like you need analytics and all those things, but you can't make it synchronous so that it makes the user experience bad. So you need to design for asynchronous processing. You have to design for API first design, right? Let's say you're making a product for something, like in our case, I made a product for video player in virtual world. Now we want to expose this to the third party creators, right? So our system should be scalable enough so that we can write some very simple APIs like play video, resume video, pause video, which a creator can come and just play in their world, right? Then observability, your design should have observability where you can add metrics, logs, traces, which are very, very important for debugging. So let's move on. So what the first thing that I use is a separation of concern. The one example that I will talk about in my project is building a global video platform. As I said, like I am working in Meta in the VR things where you can go into an event and see the video playing. Like one example is in December we played the Coldplay concert in both VR and mobile, which was 180 video playing in 3D formats, 2D formats, all those things. So our system should be good enough to scale for these many concrete users so that all the users have good video experiences playing in the live video format so that it is synced across the users. You don't want like one user sees the video 10 seconds ahead, the other is like 10 seconds just back. You don't want those type of experiences. So first thing that we developed is the ingestion layer. So before that, like we use the third party creators where we uploaded the video and all those things. So there will be like uploading layer or that thing. Second is the ingestion layers, right, which accepts the event metadata, URLs, formats, and all those things. Second, then we move on to the orchestration layer, right? Now, orchestration layer is the layer. It's just a platform component which gets the data from the servers, like, okay, we want to play this video, this is the time that is there, and all those information, what type of video format is there, what type of other informations that is there, what type of regions are there, if there is any restrictions are there or not. And then based on those information, this orchestration layer decides which SDK to be used to play the video. Let's say like in our case, in mobile we used VLC, but in VR we used different hero player. So now based on the device we decide, okay, this will go over the VLC, or this will go for this user it will go to the hero player and all those things. Then we have the rendering layer. Now surfaces, each surfaces can have different things, like iOS will have their own rendering logic, Android will have their own, VR will have their own rendering logic. So you need to decouple these things so that rendering layer, based on their use case, they can try to render what they want to render. Then, as I said about synchronization service, right? You want every user to see when they are in the events, let's say there are 100 users in the event, you want every user to see the video at the same point. let's say you are seeing a live football World Cup, right? You don't want to see like one user started jumping, oh, it's a goal, and then the next user sees it out 30 seconds. That's like a very, very bad experience, right? So we need to have a synchronous which handles across multiple words, ensuring that users see the same content at the same time with the highest resolution possible. Then there's fallback mechanism. If everything goes bad, you don't want your system to crash. You should have some fallback mechanism. Let's say showing the highlights or something else, some ads or something for some seconds, so that you show the user like something is going bad, but we are trying to handle it. Next is the pattern that I used is the real-time analytics, right? And analytics might be given afterthought in the whole, especially the software engineering, the engineering for want to work on the cool features, cool products, but this analytics is very, very important and perhaps one of the most important component for any project to be successful. Like in my case, for the video thing that I discussed, I added more than 85 metrics in my thing. That includes which includes the information at per second basis, like what video, whether the video is playing for the user, how many percentage of users are seeing the video or not, whether the video is playing or not for them, if it is buffering or not. If let's say more than 10% users are seeing the buffering or not seeing the video, just trigger us alerts based on it, right? So that the on-call can take why it's happening. And this it can be overall, it can be per event, per world, right? And the obviously number of events that analytic event that will be released will be very, very much, because it's for all the productions, for all the users. Like 200k is for one event that is running right now. In parallel, there are hundreds of events running across the environments, production, staging, testing. So your event system should be able to, analytics system should be able to handle these things. And then you should have a dashboard which probably, I think what we need to do is divide on the use case, like the users. For product managers and directors, you want a simplified dashboard where you can set out, okay, these are 2-3 metrics and this gives us me an information whether the video is playing successfully or not. That's it. But for engineering purpose, we might want to have some detailed informations, like what are the error got, what is the frame rate, why, if we can get much more informations based on that, right? And then obviously, like since there is real-time analytics, we can make a decision, do we need a sampling or not? If it is, if we need sampling, if it's okay with sampling, we can try to use a sampling of, let's say, 80% reduction, 10% reduction, whatever you want to do, right? The third pattern that I used was the multi-region deployment pipeline. Obviously, like when you build any products, you need to deploy it, and you need to deploy it for the users who are for millions of users, concurrent users that are there, right? So the thing, and it will be deployed across multi-region. So how do you deploy it? The best thing is you start with the region which has the least number of customers and try to watch there for start with 5% of traffic first, 115 minutes, 1 hour, 1 day, whatever your pipeline, and then gradually increase to that region, lowest region, and then move on to the next upper region, so that you can, even if your overall deployment takes 2 or 3 days, that might be okay, but you have the confidence whether it is breaking or not, right? And your whole deployment pipeline should be automated most probably, and should have some automated rollback system as well, where if any region it fails, it creates a save where on-call can take a call whether they need to do a rollback and all those things that are needed to be done. Now the fourth thing that I used, and this is probably one of the most important thing that I will say, because it's actually pretty simple, but it can save a lot of money. All right. So any software engineers who want to make an impact, they generally think, okay, I will make this big project which has 10 of services, it impacts millions of customers and all those type of things. But sometimes a very big impact can be done on by doing very minimal thing. Like one of the things that happened with me when I was in Adobe is we had a API which stored the data in the raw format in S3, right? And the events that were coming was millions of events. So per day, it had terabytes of data that was written, and we were concerned about the last 30 days. Now the thing was, when the initial design was done, we used S3 because we thought that okay, this will have a lot of storage, but not that much write API, read API call. But the problem was it had a lot of cost because we didn't consider many things that needed to be done, right? Now, because I was an on-call engineer, I saw others were like, okay, with the increase of the data that is coming out is getting timed out and all those things, what we can do. Then the thing that we did is like we try to see the couple of technologies that we had, like what is S3 the right choice that we want to go ahead. Can we move on to the Dynamo because we are like, okay, read write cost is cheaper as compared to S3, but storage is costly, right? So what we can do? So the thing that we did very simple thing. We compressed the data and store in DynamoDB, and at the client side we had a logic before writing into the DB, just do the what I can say, reduce the size of the data by compressing the data, right? And then when you get the read call from the data DynamoDB, get the data and then decompress it. Now, couple of things that it helped us. It reduced the size by 75%. So the storage cost that was a concern in DynamoDB, that was reduced, right? Because the data size has reduced. But since read and write API calls were expensive in S3 as compared to DynamoDB, so that overall saved the data for us. And like for cold data, which was like more than 30 days old, we moved into the S3 Glacier, which was like, because the data read was very less on those data, so we used the S3 Glacier, which are like very less storage cost. Now what it helped us is, it helped us in saving more than $200,000 on an annual saving, with storage reduction of 75% and latency reduction of 60%. And do you know why the latency was reduced? Because now since we have compressed the data, so over the network call, that was data that needed to transfer from DynamoDB to the client is less. So obviously it takes less time to get the data. So sometimes even if you make a very small change, it can have a very big impact that you can show. And you always don't need like big projects to show a big impact. Even on small things, you can do a big thing and save a lot of money for the company. Now, one other thing that I want to talk about, and as I said, like whenever you work on a project, you should not say your project is complete if you do not have an observability and monitoring thing in your project added. Because if your project has some issues for the end users, how will you know, right? Because there's no way to know if there's no monitoring, no metrics tracked, no alert tracked. So when you design a project, when you plan a project, so there should be that, okay, these are metrics that I'm adding, these are dashboard that is there, and there's alerts that will be added. The alerts can have different levels as well. It can be, let's say if it impacts just less than 10% of users, you can have it's a level 2 alert. But if it impacts more than 15% of users, it's a level 1. And if it's by like, let's say more than 25%, you can create a SEV, right, which can track it. As I mentioned, like I added more than 85 metrics in my for my video use cases. There were like more than 25 real-time dashboards that were there. There were logs added, which we can do, and some of the alerts that I had added, like this was like added, which let's say in my case, if I want to have, which is a task that is running, but it's running for a long time, so you need to have these jobs which expected duration and create a alerts for create a on-call ticket for the on-call to component. Similarly for long active failure, not if the task is not running, and right. And the best practices is you need to have alerts on symptoms, just not on causes. Like as I said, what is a user at the end? If you are building a user facing product, or if you are facing even an internal product which is used by your internal team, you want to see what's the impact, and that defines the level of the issues. Let's say if it's just impacting 1% of users, that will be less prioritized. If any other alert or any other issue, even if a small is impacting more than 10% of users. So if it is impacting more than 10% of users, numbers always succeeds. That is more important. The other thing is, you should create an alert system which prevents the alert fatigue. You should try to deduplicate the alerts. Let's say a node gets down, right? Now, if a node gets down, it will create hundreds of alerts, right? So the on-call will, instead of fixing the issue, it will try to get a call for, okay, there are 100 messages or calls that the on-call will get. But that is not a good system. Your system should have a deduplication logic for the alerts, right? Which can create 1 or 2 alerts at max for the on-call to take, and then it can have different hierarchy where it can notify to other levels. And the third thing is not just adding the metrics or not just creating the alerts is not the finished job. You need to have a actionable context of the text or alerts that you're trying. You need to have a run books, documents on how to fix it, what the on-call need to do, because the on-call, when an engineer is on call, they are looking into different pod works, right? So you as a feature owner needs to provide the actionable context, somewhere the run books, what are the metrics that it can look, what is the dashboard, what action does it the on-call can take before they try to add you, because it will make your life easier as well as the on-call life easier, and it will reduce the time that it takes to fix an issues. So this observability monitoring should be a part of your project that you're working on. It should not be an afterthought, and it should be as detailed as possible with thinking on how we can do it, because this at the end this helps. Okay, now the thing is, one of the things that we need to take about is handling a state in distributed system, right? How do we do it? So one of the things that is the challenge is the synchronization challenges that is there, right? As in our case, when I said that, okay, when you play the video, it should be playing at the same time, at the same state for all the users. But one other thing, and you might need to do some custom logic at your client side. Like for my example, what we do in case of video is we see, okay, this is the point at which, let's say at x is equal to 10 seconds, the video should have been displayed for the user 10 seconds at that point of t is equal to 10 seconds. But when the user is watching, let's say at 9.5 seconds, right? We try to add a logic in our code where each second we see at what state the video should have been watched and what is the current state that user video is watching, and we forcefully move the users to at t is equal to 10 seconds, right? Adding some custom logics, adding some buffers and all those type of things. And that's how we maintain the synchronization across the users for in case of video. So you might need to do some sort of custom logic as well, and that is a big challenge, right? The other thing is that we have used is our design should be design API that we design should be for scalability. Like in our cases, when we started working on the video thing for VR or mobile, we were the only user. We were like first party users. Now, since our product is big, we want to open this, and so that every third party creators can come and create their own world, add the video, play their own videos and all those things. The biggest challenge is if our code were not generic enough, where we can add a wrapper on top of it by, like, as I said, adding some APIs like play video, pause video, and all those type of things. If our system would not have been modular enough that we can do this, then this would have created a log problem and long project. So we should always design our API for scalability, keeping in mind some of the feature use case that can become there. We know that many of the projects that work in a big product companies have tight deadline on all those things, but we should also think of the better engineering perspective of feature use case scenarios, so that you don't need to rewrite things by default. Other thing is you should have some paginations, like if you are seeing some want to show some views on top of the video into the UI page. Let's say in our case we want to show, okay, these are the videos available for you in your catalog, and let's say if there are 100 videos, we don't want to load all the 100 videos data at the same time, right? Because of the metadata load and context, and to be fair, not many users will load all the 100 data, so we might need to do some paginations by default. It's a similar thing that you can see in Instagram for reels or media anywhere, right? You should have rate limiting, because It can be divided across the APIs, different logics and different thresholds for APIs, different partners like internal might have different rate limiting, or premium customers can have different rate limiting. You should have flexibility in querying, right? And you should have idempotency like keys wherever needed, right? Now, the other thing that I want to talk about is data processing at billion record scale. Okay. So I worked in, as I said, I worked in Adobe, where I worked in personalization experience, providing personalization. Now the Adobe had more than 3 billion user data. Obviously, these users might not be unique. They can be like org ID, contract ID, and all those type of things can be there, right? And one of the things that I had was initializing these records for org. Like, let's say we want to target 10 org, and which can have multiple employees on all those hierarchies, right? And our contract, and we want to just give them promotions for those users. So our system should be, because there's a big data scale, it can have like billions of records as well, right? So you might need to read the data, okay, which are the billion user that you want to target, not target, and all those type of things. Or let's say you want to target the users in US, that can be like millions of users, as I said. So here we should see how big data processing works. We should see how distributed job framework works. We should try to see if we can use the multi-threading in there as well, and how that multi-threading will affect the CPU usage and all, memory usage and all those things. We should have a failure mechanism, a pretty good failure mechanism. Like, if let's say if there are 10 million records that you want to process, and now you have processed 7.5 million records in the job field, do you want to retry those 7.5 million records as well? What's the state and all will be there? Will that be marked as processed or not? So you need to have all this recovery mechanism. Your system should be stable enough to work on a larger scales, even if it runs for days. But yeah, you should try to parallelize it, and in our case we did parallelize it. We try to use multi-threading, workers and all those type of things. We try to maintain, like, if the job fails, whatever it has processed, it skip those. You don't need to make, because obviously then for those you might need to make a data DynamoDB calls and all those type of things, and this helps us reduce the processing time on an average from 3 days to 6 hours, right? Now, other thing that I worked upon is the compliance and security for the projects. Like, one of the project that I worked upon is in Google was the FedRAMP compliance for the different stacks that we had, because we had more than 40 repositories, and that's what I wanted to touch upon over here as well. We worked on microservices, but one of the thing that was there, we did too much microservicing over here, and it created more than 40 repositories. And now the problem was maintaining these 40 repositories. It's not just like, okay, it says for microservices, you can have a different repo, different language, and all those things. They will have their own deployment and all those things. But the thing is, if more than 40 repositories, if these type of things comes where you have to maintain the compliance and all those things, you have to work on the 40 repositories. In your daily life, you have to maintain those repositories. You have to maintain the deployment cycle of those repositories and everything, right? So we need to make a decision that, okay, do we need this much microservices? Is it just distributed monolith? We are like, okay, can we merge these two, three microservices into one, so that our number of repositories can reduce from, let's say, 40 to 10? Because for each function, you don't want to go ahead and make a new repository, right? That's not a good design, because again, it's an engineering overhead. It's an engineering hell to maintain these repositories, right? And if something like these comes up where there's a compliance thing and all those things, you have to do this for all the repositories that are there, and their testing and all those things, right? So that can become a very big challenge. So for me, what are the lessons learned, and what are the anti-patterns? As I mentioned, one is the anti-pattern is a distributed monolith. So just imagine, as I said, like there were more than 40 repositories, and in Adobe we had another like 100 repositories or something like that. So do we need this much repositories and this much microservices? Like, if there are or is it just like a distributed monolith? Like micros that are tightly coupled and they must be deployed together. They are like combining the worst of both the worlds instead of best of both of the worlds, right? You're making a microservices, but you need where you have to make the deployment challenge and all those type of things, and then again you have to make sure they are deployed together in the orders and all those type of things. It can take a lot of time as well. So this is like one of the things that is not there. Again, shared database, and the other thing that I talk about alert fatigue. Like, let's say if we want to have a CPU usage less than 95%, and then we track an alert. So if on every CPU spike if happens, right, then what will happen is it will get a lot of alerts, and on-call will start ignoring it, right? So your alerting and metric system should be such that there should be no fatigue alert. You should have deduplication logics. You should have the metrics that you create or the rules that you use to create alert should be not too what I can say, picky or something like that, so that it creates alerts on every small things, but it should not be too broad as well that it does not pick up. You should have a good balance of it, right? So one other thing that and the other thing, like the proven practices are, you should always design for failure your system. You can assume that hardware will fail, network will fail. You should have retry logic, circuit breakers, and fallback from day one. That should be part of your design, right? You should have your observability first. This should be part of your design in a project. You should not shift features without metrics. If you can't measure it, you can't improve it or debug it, or you will not know what happened. Let's say something bad happens and you know it after 6 hours or 1 day. So that's very bad, right? So what are the features of scalable architecture? These are like serverless and edge computing, right? That we are seeing right now. AI and intelligence scaling. We are seeing that now. We are seeing right now, even in coding, we are seeing using all the Claude and all those AI which helps us because those are helpful in giving us the code or the architecture of the system that are there, right? So that is also like part of the scalable architecture because it helps you speed up your development. It helps you in code review and everything, right? It helps you in better onboarding things. So that can be also a part of it because it improves you. You need to develop platform engineering and right, and you have to take about the cost, performance, and architecture constraints and all those things. So what are the practical recommendations that are there? So what I do is I will say that you should always divide into 4 different phases. First is the design phase. In design phase, basically before that you need to see the use cases. What are the use case? Why you are building it? By when do you need it? And all those type of things. What is the impact that it will have? Right? You don't want to build a very complex system and the impact is less, very very less, and want to spend 6 months. Right? That's very bad thing. Like the example that I gave you, where we save $200,000 in a year. Right? That project can be like 1 week or 2 week project. So that you can prioritize that before taking a complex project which has less impact. And after that, if you design the project, the next thing that you want to do is design phase, right? You should not build any complex system until you actually need that complex system. Like an example, don't build microservices until you have microservice problem. In our case, we had more than 40 repositories that some of them could have been merged, so we don't need it, but it was there, not there, and now we have to maintain it. It's an overhead for on-calls, for engineering purposes, for engineering ops, and all those things. And you should always assume every component will fail. Every small component can fail, and you should have a fallback over there. It can be on the operational thing, by the logic side as well, right? And the operational thing as well. Like if it fails, you need to have a metrics, observability, and all those type of things. You need to define SLAs, right? And come on a compile. Like you can't go and tell the product managers, okay, this is a system I have designed, and the user will see it, let's say after 1 hour. And let's say the project wanted, no, this is a very bad thing. We want the user to see it in 5 minutes. So if you develop everything and this latency and all those things are not clear, then it's a very bad thing. You should have an implementation phase. And implementation, you need to see what are the things technology that you can use, whether you want to use the sync technology, async technology. You should have um, idempotency logic. If you, obviously there was something called retrying logic will be there. You will have circuit breakers and all those type of things. So retrying operation should be safe and it should have been side effect free. Try to keep the server statelessness, because the users stateful servers, obviously the challenge with them is like if a user request go to another server, right? Then how you don't know the status, or that state, that server itself goes down. So that makes a very difficult to maintain the stateful service. You should always try to go for a statelessness server as much as you can. You should have your testing strategy, right? You should have everything. You should have a load test done. You should have a performance test into your CI/CD pipeline. I, I don't know if you know about chaos engineering, like Netflix generally does it. It every day tested by killing one of the servers at randomly and see if Netflix is working as expected or not. All right, that's their like chaos engineering, where they break things to see if it's working or not. Uh, and you should always, before moving into the data in production, you should always test it, whether by load testing or anything, by creating some mimic data and all things with the production scale data sets, not just let's say five. Like for us, an example is there are 200,000. You have want to design an events where 200,000 concurrent users can see the event in 3D formats, right? If we did a design of five, let's say five users or 10 users, and if you go in production, it will, there are more chances not that will start breaking, because the users can be on different locations. There can be CDN issues and all those things. There may be network issues. So you should always test your systems on a production scale data sets, right? And you should have, in your project you should have your operations defined, right? You should have a logging, distributed tracing. You should have automated recovery system that can be a scripts which should fix known issues. You should have run book where you can mention, okay, this is how you can run the scripts. Or even better, if it fails, you can try to automate the system, try to do all those things. So yeah, these are things that I wanted to discuss today. Thank you for your time. Bye bye.
Yeah, that was great, and actually, thank you. Let me pull up my speakers here from the backstage. And hello back, Asif. Hello,
So
Raj. And I hope Nikita. Yeah, you can. You hear? Okay, cool. Thank you for these presentations. And Asif, I was saying thank you for sharing this concept, because for like the last 5 years, I always hear microservice, microservice, more microservices, and everything. But for like last maybe year, quietly I hear from guys like, I can't handle that much actually, and that
yeah,
we can't afford more DevOpses anymore. So actually we get a problem or something. So thank you for saying this. It's very important. And yeah, let's get that fun, because I have some nice questions, I guess, if you don't mind. So why don't we just start from this question for you, Raj? If your system becomes 99% reliable, won't users stop reading the notes carefully? How do you design this interface to force active verification?
Yeah. So that's a good question. So basically, if high reliability can make sure the trust, user trust the system, right, too much, then we kind of skip careful reviews. Like for example, which is very like which is very risky in critical domain like healthcare. So basically, to you keep user engaged in verification, the interface should require active participation, not just passive confirmation. So basically, active participation from users should be required from uh like in my case, physician, when it checks all the things that is stated by the agent, right? Then the some of the things that design patterns that should be taken care of is could be like highlighting and flagging uncertain or critical section that needs explicit review, right? So like to basically align the pattern with the experience in like medical scribe system, where every claim is mapped to a transcript evidence, right? And unsupported claims are flagged for users attention. So this kind of like systems helps in like even if the system is 99% reliable, you need to have an interface that you force actively forced to verify the notes, because in healthcare, I'm not sure, in I think in other compliances also, like insurance or finance, they will have similar problems where every step is kind of guided by compliance. Like every note that the AI agent describes is a part of a documented entity, and that documentity is auditable, and somewhere someone is accountable for it.
All
So
right.
that requires, like, more verifications, even if it's 99% reliable.
Yeah, but how do we actually build this new normal? Because, of course, at the beginning of my working day, I read everything it generates, I read all these diagrams, and I actually into that. But when it goes like 6 hour, or it's maybe after the midnight and I'm tired, I just go next, 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 because, well, if something wrong, I will probably fix it later. And this builds even more technical AI generated depth or something. I can imagine in different other spheres the same behavior, when people just getting tired to read all this, and they go like, come on.
So I
Yeah.
believe in that, you need to have, like, as you said, if you're tired and you just follow whatever the instruction is provided, you need to have strong, like, verification council of judges, right, in multi-agent systems. So you need to have, let's say, your grounding agents, your behavior agents, the grounding agents that maps the claims for evidence. Then you need to have behavior agents that needs behavior agents is basically deterministic calls of all the tools that were part of your process. So whether all the tools that were part of plans were kind of executed, whether all the metrics that were logged kind of aligns with the evidence that you have. Then is also something called debate judges, where for every claim that is covered there, there's a critic section of the debate agent that kind of counters your claim. So all of this needs
Mhm.
to be in place of your pipeline, so that as a tired agent also, the all this verification, different verification council of judges, which is not technically just LLM method judge, it can have deterministic calls as well. So all of that is available for you to see in a, and maybe in a telemetric style kind of log, so that even at tired you can just see the important things and decide for yourself, right,
Yeah.
where and what went wrong, and like, not went wrong, but what's the diagnosis of the system altogether.
Yeah, well, it's very complex and interesting part when it comes to psychology and human machine interactions. Yeah, thank you very much, and we're moving on to you, Nikita, with next question. How do you manage contract drifts across different teams? If the data engineers change a feature specification that technically meets the contract but changes the physics of the model relies on. Wow, I don't even follow the question.
Yeah, good question. Yeah, first of all, maybe let's talk about management contracts between different teams. It's a classical conveys law. We need in order to detect drift, in order to manage contracts the same, it's a good idea, for instance, to have a common repository for each contract, and having these, let's say, ground rules for each artifact you're using inside your system. It's must to have, because we almost using the same practices, the same approaches in a classical software development. But the biggest, let's say, issue, the biggest gap, that we are, let's say, ignoring things we already know for a classical stuff with building AI solutions.
Right.
Yeah, so just have repositories, and from times to times you need to make a review of your contracts. And let's say once, for instance, your contract significantly drift from the real physics, you will see it from the behavior of your model.
Yeah.
So you need to have a
Or
proper
some
monitoring.
signals on
Yeah.
MD. Yeah.
Mhm.
All right, cool. And next goes to you, Asif. How do you prevent deployment drift? that was a typos I made. I'm sorry. In a multi-day rollout, if a user in a new region sends a request to a service in an old region that doesn't yet understand the new API schema, let me change
Yeah,
it.
I think what we need to have is, as I said, in the APIs and all those things, whatever we develop, there should be a versioning mechanism as well, where you can say that what version of the API that are being used, right? And even in multi-day deployment, you will have some versioning, which version you are using, and all those things, and that will most probably help you in uh, mapping what which one to use, and based on that you can get the correct response. So that's I think how uh, we should work more. Like, okay, from the old region you're getting, let's say, v1 version API call, and you are trying to deploy v2, but you will have the version history as well, v1, v2, and all those things, and based on that you can make a mechanism. Like, for an example I can give you, we developed the video player in the immersive worlds and all those things, and we exposed API to the third-party creators. But we always make sure that whatever API that we develop are always backward compatible, so that it does not break the backward thing as well, because needs to be used by anyone. As I said, there can be deployment times across the regions, creators, and all those things can be there. So an API should always be backward compatible with versioning and everything that needs to be there, so that it does not break the things in production. Like, even for example, deployment or all those things, you can use the API, let's say, via an Android app. Some users can update the app, some will not update the app. So you don't want the users who are on the previous build to break the experience for them, right? So
Okay.
should be there.
Okay. Thank you. Going forward to you, Raj. But if the validator is also an LLM, uh, can it fall into the same hallucinations? How do you prevent the validator from becoming overly agreeable? Well, and you are muted, probably.
Sorry, so I was saying that that's a very question, that's what I was kind of answering in the last comment, wherein you have validators council. You just don't have validator one validator, and it's not just LLM as a judge. You have a council of validators. For some example, in production systems, that I typically suggest is like four kinds of validators that we follow. One is the deterministic one, which is the grounded validator, right? So basically, uh, uh, if the claim is correlating to an evidence, those are like regex match and schema matches that we can do. Those are deterministic ones. Then there are, like, debate judge that I mentioned before, is kind of LLM as a judge call. If there is some contradiction between two agents output, then what needs to go forward, that can be LLM call. Then there is like a behavior judge, which checks for different tools. So we have, in case of agentic setup, you have a plan that you need to follow, and you have different tool calls. So basically, when the plan is created, whether all the tool calls were called appropriately, or if some important ones were missed. So these are also very deterministic calls. And then in terms of your own LLM validations, as a judge, you can have different modes of validations, right? You can validate some, for example, you can validate your output directly, right? You can validate your entire system flow. You can also validate in terms of external validation. So you can have your own set of, for example, if you're building some kind of chatbot, so you can have like a Google web search kind of generation through ground truth, and then you can have your LLM judge that. So I would
Mhm.
say, just not rely on LLM as a validator. You have your deterministic check as well, that test both your system, the processes involved, and the final output. So
Okay.
that gives you a more of a reduce hallucination at all levels, right?
Yeah.
So I think having a council of agents for judging helps in that.
Yeah. Thank you very much, for sure. As if with 85 plus metrics per second and dashboards, is there a risk that engineer will only look at the charts they personally build? I love it. And you are muted.
Sorry. So in my use case, yeah, what I built was I thought of this dashboard as two different set of users, even within the company, right? One set of users were just wanted to know about the basic things, like whether the video is playing correctly or not, what's the resolution. That's it. They don't want to get into the depth of all this. Let's say a basic dashboard, which will have 4 or 5 different columns. So that any users can come, let's say director can come, product manager can come, who just want to say, okay, for this event, what was the experience? They can add the filters and all those things. They can say, okay, whether the experience was good or not, something bad happened at what time, and then they can ask you. Then there was different set of users added much more detailed information where we, the engineers, whatever engineers who were in the pod, who had much more technical information, go and look into this. So we always thought of dashboards being used by two different set of users, which can help us first to understand what was the experience was, and the other which will help you in debugging, which was like core engineering expertise. Like as an
Okay.
I want to know what was the frame rate that was happening and all those things. If an exception, what was the exception that happened? How many users face this type of exceptions and all those things. But let's say the director or the product manager do not want to know this. They want to know whether the video is playing or not. That's it.
Okay.
So that's how I vision this, to see that there were two different set of users. One was a basic dashboard with 4 or 5 graphs. One was much detailed information where me or anyone in my team can go and see what's happening.
Thank you very much. And Nikita, to you. How do you version control the relationship between a specific model and specific policy? Again, version control.
I suppose the question also contains an answer with the help of version control repository. So as I said in my presentation, you need to have a contract between your boundaries, and the best way to control consistency, to control versions, is just to store these contracts in some kind of repositories. Yeah,
But I mean, how do you structure that repository and maintain it?
just since the contract, it's a Python code, it's just a code you just commit, and it's with the help of native tools of repository, you can check differences between different versions of contracts. You can use the whole process of, let's say, versioning control of this life cycle of each contracts. Yeah, it's the same approach we have with the classical software development.
Okay, thank you very much. And moving on, Asif, what is the microservice threshold to prevent a distributed monolith? Is there a specific quantitative rule that you use to decide when two microservices should be merged back into one?
Yeah, I think it should look onto the pros and cons that you are having. Let's say if the operational overhead is much more than the use case that you are trying to find, and also like let's say if you've developed something and you know that okay, I need to deploy these two microservices together, all these things that can be there, and you can see that okay, they're actually not two different microservices but just one microservice which is like there. So probably based on the pros and cons of the use case that you have at that point, and see what the overhead that is happening for you, then probably you can make a decision. Okay, was this the correct design that we took to make like let's say 2 or 3 different microservices? Can we merge it together? Because at the end there can come where you have to do some operational work, and that will be a big pain. As like I saw in my experiences in Google and Adobe, like one project we had 40 different repositories that took a hell lot of time that it actually should have been, because some of the things could have been much, because literally in each of the microservices there were like 1 or 2 APIs that were exposed and being used, and similarly other microservices 1 or 2 were there, but those could have been merged. So it reduces the overhead. So yeah, that's what I think we should do to see what pros that you're getting. If the cons are higher than the pros, then probably we should merge it.
Thank you very much. And to you, Raj, your architecture relies on linking every claim to a specific text span. What happens when diagnosis is simply is implied by the doctor from the context, but never explicitly spoken in the audio?
Yeah, I'm just reading the question. So, what happens when the diagnosis is implied by the doctor from the context, but is never explicitly spoken in the video? Yeah. So, this exactly is what I would say is error in terms of in doctor's diagnosis, right? So in my architecture, what we have is like every claim must be explicitly linked to a specific text span in the transcript. And I have also ensured traceability and reliability in this frame. So if the diagnosis is only implied and not like explicitly stated, then the system will not generate that diagnosis as a claim. So for example, and if the doctor goes ahead and still validate something, that's the doctor, like a final thing in our pipeline is the doctor's recommendation. Our thing is to just give the audio and the soap notes so the doctors can make a healthy out decision. So there are two cases. There could be something like doctors genuinely, like as a human, genuinely kind of evaluated it correctly, but or diagnose the disease correctly, or second thing that can be the doctor was ignorant to the fact, and he might not have looked at the soap notes, he might not have looked at and maybe have misdiagnosed it. So I think our system is designed in a way that it reduces the second scenario as much as possible, because we have everything in place, traceable, reliable. We have the soap notes, we have our different categories of symptoms, vitals, all the schemas are clearly stated in the document. So it's very difficult for doctors to still misdiagnose it. But yeah, if it they can, then it's just like, I think it would be just an human error in that case.
Okay, guys, it's just tech. We have our constraints, and it's okay to actually admit it. Thank you very much. I'm not sure, Nikita. I have another question, but I think it's still the same question. It's just about like having some uh, version control and shared space. So I will not spend our time on that. I will just say thank you for your experience and energy, and for being with us, smiling, and sharing with the community. I will be expecting you for our next sessions, our next chapters. You know, to wrap up, I would say these days, like I feel, of course, this is my bubble, but I feel that the the role of community is even growing at the era. And I feel like the community has to be this kind of boundary or guardrails for what actually AI generates, right? Of course, AI getting kind of smarter, but it already knows all the internet, right? So it can't get wiser. But we actually moving on, we have this knowledge and wisdom from experimentation and failures and everything, and we can guide each other and share this knowledge and experience, and that's where I see the Giggle and other communities place in the future, because the theory is great and the ChatGPT delivers knowledge just when you need it, right? Just in the situation. But is it the best knowledge? Is it the wise answer? Is it the best decision, or just because like more text about that on the internet and it thinks like this is the best one? All right, thank you very much for contributing in this, and have a nice day, evening, or morning, whatever you have there, and see you next time.
See you.
Yeah, thanks a lot.
Thank you. See you.
Thank
Yeah,
you.
have a
Bye.
nice
Bye,
one.
Brian.
Bye, guys.